Okay, so we're going to be using the chain rule today to connect together rates of change. Okay, so hit pause, copy the lesson objective down. When you're ready, hit play, and we'll look at an example. Right, so as it says here, you need to be able to use the chain rule to connect together rates of change, and we're going to apply them in real world contexts. So here we've got area of a circle A. It's related to its radius by the formula A equals pi r squared. Very good. Seen that somewhere before. And the rate of change of the radius is given by dr by dt. So it's the rate of change of the radius with respect to time. Find the rate of change of the area with respect to time, dA over dt. So we want to find dA over dt. Just quickly have a look here. We want to find dA over dt. And we're given dr by dt. So I've got my dt, but I need to find dA by dt. So using the chain rule, I've got the area here. If I differentiate the area with respect to r, the radius, dA by dr, then I've got my dA by dt. Because dr, I can cancel my drs, leaving me with dA over dt. So this is what I'm going to use then to help me find rates of change of the area with respect to time. So let's have a look at what we got. We got A is equal to pi r squared. That means that the A by dr is going to be equal to 2 pi r. Very interesting. Rate of change of the radius, of the area with respect to the radius. I've also got dr by dt, which is equal to 5. So I can find my rate of change of the area, which is going to be equal to dr by dt times dA by dr, which is equal to dr by dt be 5 times 2 pi r, which is equal to 10 pi r. And when the radius is equal to 3, the rate of change of the area is given by, when r equals 3, dA by dt is equal to 10 times pi times 3, which is equal to 30 pi. Okay. So that's a pretty straightforward example. Hit pause, copy the example down. Once you've done that, hit play and we'll look at another example. Okay, so let's have a look at this example we've got here. It says the volume of the hemisphere V is related to its radius r by the formula V equals 2 over 3 pi r cubed. So we've got V is equal to 2 over 3 pi r cubed. The surface area is given by the formula S equals 3 pi r squared. So S is equal to 3 pi r squared. Given that the rate of increase in volume, so the rate of change of volume with respect to time is 6. So dV by dt is equal to 6. Find the rate of change of the surface area with respect to time, ds by dt. Okay, now I've got V equals 2 over 3 pi r cubed. I can find the rate of change of the volume with respect to the radius, dV over dr. And that's going to be, if I multiply by 3, I get 2 pi r squared, because the 3's cancel. I can find the rate of change of the surface area with respect to radius, ds by dr, which is going to be equal to 6 pi r, and I've got dV by dt equals 6. Now I need to find ds by dt. If I just write that here, I've got to use the chain rule. Well, I'm going to use the chain rule to help me. So what I can do is use what I know. I've got dV by dt here, dV by dt, multiply that by ds by dr, because I need to find ds. So it's ds by dr. But I need to get rid of the dv and the dr there. So if I multiply this by dr over dv, then just change color of the pen here, and that means if I cancel my dv and I cancel my dr, I'm left with ds over dt, which is what I'm trying to find. So that's going to work for me. So ds by dt is equal to dv by dt times ds by dr times dr by dv. So if I sub what I've got, dv by dt is 6 times ds by dr, 6 pi r, times dr over dv, so that's going to be 1 over 2 pi r squared. And I can cancel then some of these terms. Oops, I want a different color. Let's go blue. 2 goes here 1 time and 2 goes into 6 3 times. Pi's cancel, and the radius here cancels with one of the radiuses here. So I'm left with, just switch back to red, 3 times 6, which is 18, over r, or 18 r to the power of minus 1. Either one is fine, and that's the rate of change of the surface area, ds by dt, with respect to time. Okay, so hit pause, copy the example down. Once you've done that, hit play, and we'll look at a further example. Okay, so let's have a look at this example. It says, in the decay of radioactive particles, so decay, which means it's a decrease, the rate at which the particles decay is proportional to the number of particles remaining. Write down a differential equation for the rate of change of particles. Well, differential equation is what we've been doing, is any equation that involves a rate of change. So, in this one it says, write down the rate of change of the number of particles. So that's going to be, if we call n the number of particles, then the n with respect to t, and it's proportional to the number of particles remaining. So it's proportional to n, the number of particles remaining. So that means we can write, if you remember from GCSE, the n by dt is equal to k times n, where k is the constant of proportionality. That was in GCSE where we did proportional to. Now because it's a decay though, it's going down, so we've got a negative equation. dn by dt is equal to minus k times n. And that's our differential equation now set up. So if you were working in science, you might find an equation like that useful. Hit pause, copy the example down. Once you've done that, hit play, and we'll look at a further example. Right, so this example, we've got Newton's law of cooling. States that the rate of loss of temperature of a body is proportional to the excess temperature of the body compared to its surroundings. Write an equation that expresses this law. Okay, so same as before, we've got to write a differential equation. If we let theta be the temperature, then we can say that the rate of change of temperature, in this case it's a loss, but that's the rate of change with respect to time, and that's proportional to the excess of the temperature of the body compared to its surroundings. So the body's temperature, say, is theta, and the difference between that and its surrounding, theta naught. So we're part of the way setting up, so that's the rate of change. It's proportional to the difference between the body's temperature and its surroundings. Then we introduced the constant of proportionality as before. D theta over dt is equal to k times theta minus theta naught. And it's losing temperature, so it's going down. So we've got to introduce the negative then. So d theta by dt is equal to minus k times theta minus theta naught. Okay. Hit pause. Copy the example down. Once you've done that, hit play, and we'll look at one more example. Right, let's have a look at this example. The head of a snowman of radius r loses volume by evaporation at a rate proportional to its surface area. So it's losing volume, V, and at a rate proportional to its surface area. Assuming that the head is spherical, that the volume is given by V equals 4 over 3 pi r cubed, and the surface area A is 4 pi r squared, write down the differential equation for the rate of change of radius of the snowman's head. Okay, that's quite a lot of information there. Let's have a look at what we've got. First off, it says it loses volume at a rate proportional to its surface area. So that means volume is V, so that means dV by dt is losing volume at a rate that's proportional to the surface area, which is A. So we can write that dV by dt is equal to constant of proportionality k times A, but because it's losing volume, that means dV, let's try and make this its volume capital V, dV by dt is equal to minus k times A. Okay, so that's dV by dt. That's our first line done. And then it says, assuming that the volume is given by V equals 4 over 3 pi r cubed, so V is equal to 4 over 3 pi r cubed. That means the rate of change of the volume with respect to the radius, or dV by dr, is equal to multiplied by 3, so we got 4 pi r squared. Okay, and the surface area A is 4 pi r squared. Write down the differential equation for the rate of change of radius of the snowman's head. So the rate of change of the radius, r is capital here. I'm used to using a small r, so r is capital. So dr, the differential equation we want is the rate of change of the radius, dr by dt. Now, I've got dV by dt, and in order to get the r by dt, I've got to multiply it by, to get rid of the v, by dr, capital R, over dv. But I've got that over here. Let's change this to a capital R. Okay. But I've got to invert it, because then, if I just change my colors to blue, these will cancel, leaving me with dr over dt. So, I can say that dr by dt is equal to dv by dt times dr by dv. And so if I sub in what I've got, dv by dt is minus k times A. Multiply that by 1 over 4 pi r squared. I know the area because it's given to me in the question. So if I sub that in, it's going to be minus k times, interesting, 4 pi r squared times 1 over 4 pi r squared. So the 4 pi r squareds cancel, leaving me with minus k. So I can say, therefore, dr by dt is equal to minus k. So the rate of decrease is constant. Okay, so I think it's time for you to attempt some questions for me. Hit pause, copy the example down. When you're ready, hit play and do some questions. Okay, so exercise 9J, it's on page 263. Off you go. I'll attach the assignment, sorry, the classwork to the assignment.